All right, everyone. This is our second lecture. We'll continue for chapter 1. Okay. So last time we discussed how to calculate the median, the mean. We stop here. Quartile is similar to median. So quartile divide the data as nearly as possible into 4 different quarters. And median is divided by data into the top and bottom halves. And the first quartile. Yes. Yes, question? So the first quartile is the median of the lower half of the data. Okay, so from 0 to the bottom 25%. Okay, so to find the first quartile, again, is similar to what we do for the median. We calculate 0.25 times n plus 1. N is the sample size. Okay. For median, we calculate 0.5 times n plus 1. So depending on the number, if this number is integer, okay, then the sample value in that position will be the first quartile. If not, we take the average of the sample values on both sides of this value. So same as what we did for median. So that's first quartile. The second quartile will be the median, so 50%, right? Then the third quartile is the median of the upper half of the data. Okay, and similarly, we calculate 0.75 times n plus 1. Again, integer, then the sample value will be in that position will be the third quartile. If not, take the average of the left and right. Again, the median is equal to 0.5 n plus 1. So that's the second quartile. Okay, so median is the second quartile. So quartile divided by the data into 4 equal quarters. Percentile divided the data into 100 different parts, 100%. Okay, so P's percentile of the sample, and P will be the number between 0 and 100 divided by sample, so that nearly as nearly as possible, P% of the sample values are less than P's percentile. Okay, so the idea is the same as quartile. And the calculation of percentile is also similar to what we did for quartiles. First of all, of course, we need to arrange the sample, n samples values from the smallest to the largest. And we calculate the value P over 100 times n plus 1. Okay, for quartile, first quartile, we calculate 0.25 times n plus 1. For median, we calculate 0.5 times n plus 1. For this percentile, we calculate this. Okay, again, if this quantity is integer, we just use the sample value in this position. If not, we take the average of 2 samples on either side. Okay, so same idea. And of course, the first quartile is the 25th percentile, the median is the 50th percentile, and the third quartile is the 75th percentile. Okay, so very easy to understand. Okay, a simple calculation. So let's say we have 5 number. Okay, 2, 3, 5, 6, and 7. Let me share my notes with you so I can write down the calculation. Okay, so 2, 3, 5, 6, and 7. So that's already arranged from the smallest list to the largest. Okay, so what is the mean? Okay, so the mean is, you know, the sample items added together divided by sample size. And the mean is the most straightforward. So 2 plus 3 plus 5 plus 6 plus 7 divided by sample size, which is 5. Okay. For the median we need to calculate 0.5 times n plus 1. Okay. And here n is 5. So 0.5, 5 plus 1. So that's 3. So that's the third sample item. So the third sample item will be this one, 5. Okay. 5. Okay. The first quartile we use 0.25 times n plus 1, and is 5 plus 1. So we get 1.5. So 1.5 is not integer. So we need to get the average of both sides. Okay. So the average of the first item and the second item. Second item divided by 2. What is the first item? The first item is 2, right? So that's 2. Second item is 3. Okay? 2 plus 3 divided by 2. Okay. So first quartile is 2.5. And similarly, for the third quartile, we use 0.75 n plus 1. We get 4.5. Okay, so 4.5 we get the average of the fourth and the fifth. Fourth is 6, fifth is 7 divided by 2. So that's the third quartile. Okay, so right, so that's a simple calculation for the median quartile. Any questions before we move on? Okay. So mode is another new definition here. So mode is the measurement which occurs most frequently. Let's see, for this set, we can see if we have 8 occurs twice. All other number only occur once. So 8 occurs most frequently. So the mode is 8. Okay. For this set, we have 2 2s. We have 2 A's. So here we have 2 modes then, 8 and 2. We also call that bimodal. Okay. In the third case, we have nothing more than 1. No number is more than 1. So we call that no mode. So mode is the number which occurs most frequently. Okay. All right. So sample statistics and the population parameters. Okay. A numerical summary of a sample is called statistic. Okay. For example, in previous example, we have a whole population of 1,000 rod, and we want to know the diameter, average diameter, and we get a sample of 50 rod, and we measure the diameter of these 50 rods. Okay, so the sample average is called statistic. A numerical summary of a population is called parameter. The average diameter of the whole 1,000 rod, so we call that one type of parameter. Okay, so parameter is about the whole population. Statistic is about a sample. Okay, so in this class, one of the major tasks is to how to infer or get information about certain parameter based on statistic. So using sample information to get information from the population. So again, the population include everything under study. Okay, for example, the 50,000 students in the university, and professor want to know the average height. So in that case, the population will be 50,000 students. And she get 100 students sample and measure the heights. So that sample will be 100 students. Okay, so we're trying to get the information about the average height of the whole university. So we call that parameters from statistics, such as the average height of the 100 students. And okay, so look at some of the population parameters. Okay. So the population mean is called mu. Okay, we can also write as EX. E is for expectation. It's same idea as mu, but we use mu all the time. Okay, so mu again is the mean value for the whole population. So that is equal to xi, which is the value for that ice sample. P xi equal to xi means P is for probability. So P means the probability for x equal to xi. Okay, so if that's equally likely event, then for every single sample item, the probability will be the same. Then we can just use the equation here on the right. So mu is equal to all the sample items added together divided by n. Okay, so capital N is the population size. Small n is for sample size. As you can see, the population mean, the equation for the population mean is almost the same as the equation for sample mean. Similar to variance. So the variance for population, we use sigma square. For the variance of the sample, we use S square. So we discussed that last time. So sigma square is equal to E, again, is for expectation, but we don't use that often, just use sigma square. We can use this equation. Again, P here is for probability for x equal to certain value. Okay. And if it's equally likely event, we simplify the equation into the equation on the lower right. So sigma square is equal to, this is xi, sample items, minus mu. Mu is the population mean. Capital N is the sample's population size. Okay. So if you remember last time, we discussed the S square, which is the sample variance. And the equation for sample variance is this. Very similar. Okay. As you can see, for sample variance S square, so it's divided by n minus 1. Why we use -1? We discussed last time because we want to use we want to estimate sigma using S. So we use -1. N is the sample size. And this is the sample mean value. Okay, so these two equations, very similar format. Again, in this class, we're trying to estimate the parameter such as the population mean using statistics such as sample mean. Or we're trying to estimate the sigma square using S squared. Okay, events. Events is another new definition here. That's the outcome of experiment. Okay. For example, if you toss the die and we observe the number appear on the upper face of the die. Okay. So we know the die has 6 faces. Okay, 1, 2, 3, 4, 5, and 6. Okay, so let's say event A is defined as we observe odd number. Okay, odd number including 1, 3, and 5. Okay. And let's say event B is defined as we observe a number less than 3. So less than 3 include 1 and 2. Okay. And we can see both event occurs when the upper face show as 1. Okay. So if we get 1, we observe a number less than 3 belong to event B. Also, we observe an odd number, so event A also occurs. And event E1 defined as we get number 1 on the upper face, E2 we see a 2, and so on. Okay, so that's all the possible outcomes for that experiment, which is tossing a die. Okay, no other possible outcomes. We see 2 events are mutually exclusive. Okay. If one event occurs, the other event cannot occur. Okay, so vice versa. So event A occurs, then that means event B cannot occur, and vice versa. So we call event A and B mutually exclusive. The event A and B, as we discussed in the previous slides, it can be further simplified into event E1, E3, and E5. So event A is we observe an odd number. So E1 is we see a 1, E3 we see a 5. Okay, so and event B, which is we observe a number less than 3. Okay, so that will include E1, we see number 1, and E2, we see a number 2, right? Okay. So we can further decompose an event until it can no longer further decomposed. So an event that cannot be further decomposed is called a simple event. For example, E1. E1 means we observe a 1. Okay. We cannot further decompose E1 into even simpler events. So E1 is a simple event. Okay. The set of all mutually exclusive simple events is called sample space. The sample space for the experiment of tossing a die, including E1, E2, E3, 4, 5, and 6. Okay, so these 6 events are simple events, and they are mutually exclusive. Okay, if one occurs, two cannot occur, and vice versa. Okay, so this is the sample space. So sample space is all the possible outcomes together. Okay. And the event is collection of one or more simple events. So for characteristical data, we can use frequencies and sample proportions. Okay, so frequency is the number of sample items fall in that certain category, and sample proportion is the frequency divided by sample size. Okay, so frequency is the number of sample in certain category. And the sample proportion is the frequency divided by the sample size. Sometimes it's also called relative frequency. Okay. So how we can graph qualitative variables? Okay. So we can use delta distribution to describe what values has been measured and how often each value has occurred. Okay. For how often we can use frequency. For example, if that value occurs 3 times, the frequency will be 3. Okay. Or we can use relative frequency, which is equal to frequency times n. So if we totally measure 10 times and one value occurs 3 times, then the relative frequency will be 3 over the total 10, okay, 30%. Percent is 100 times relative frequency. So 100 times 3 over 10 is 30%. That's the example. Go back to my computer. Okay. So we have a bag of M&M candies. Okay, totally 25 candies. They have 6 different colors. Okay. As you can see from here, we can first we see how many different colors, and we list here in first row, and we count for each color how many candies there. Okay, we have 5 red, 3 blue, and so on. So the frequency is how many times that event happens. So red occurs 5 times. So the frequency for red is 5. And the relative frequency is frequency divided by n. So the total number of candy is 25. So 0.2 is the relative frequency, or 20% as a percent. So we can do this for other colors as well. Then we can plot this into a bar chart, and all right, since I cannot display this well. Sorry, let's go back to my notes. Okay, we can see here. So we can use a bar chart or a pie chart So the bar chart is the upper left. So the x-axis shows different colors, 6 possible colors. And the y-axis shows the frequency. For example, for red, it occurs 5 times. Okay, so that's simple bar chart. Or we can use pie chart. Pie chart shows the frequency. Frequency, for example, red occurs 5 times or 20%. Okay, and in all the possible colors, the percent added together is equal to 100. Okay. So pie chart and bar chart are very often used. Okay. Let's further look at some other charts. Okay, some of them are used pretty often, such as a scatter plot, or histogram, or box plot. Sometimes some of them are not used very often, such as dot plot and the stem and leaf plot. But anyhow, we'll give a short introduction for each of these plots. Okay, the first one is stem and leaf plot. Okay. So a stem leaf plot is an easy way to summarize a data set. Okay. So each item, each value have a stem and also has a leaf. Okay. A stem consisting of the leftmost 1 or 2 digit, and a leaf consists of the next digit. Okay. Use the stem and leaf plot, we can see all the values, and also can give us an idea of the shape of the data. Okay, as in this example. So this is a data showing the duration of the dormant period of the geyser Old Faithful in minutes. Okay, so Old Faithful geyser is the very famous geyser in Yellowstone National Park. Okay, so they have eruptions for every certain minutes. Okay, the time between 2 eruptions, consecutive eruption, is called the dormant period. And this table summarizes the dormant period in minutes. Okay, showing us all this data. Okay. For example, 42 minutes, 45 is already a range from shortest to the longest, which is 93 minutes. So if we plot this data into a stem and leaf plot, for example, 40, we have 3 times, 42, 45, and 49. Under 50, we have 50 here, and we have 51, 51, 51, and 51. So which means we have 1, 2, 3, and 5 51. So 4 of the dormant period of 51 minutes. We all list here. We have 2, 53, and so on. Okay, so we can do this. You get an idea for all the dormant period from this table. Okay. So the stem and leaf plot can display all the sample values, as we can see from here, and we can easily reconstruct the data using the stem and leaf plot. So another example, this is the price of shoes. Okay, $90, $70, and $65. So we have these values, so we can, just use this value to make a stem and leaf plot. So 40, 50, 60, 70, 80, and 90. Okay, so for 40s, we have only one value, which is 40. So no other. Under 50s, we have nothing. Okay, so we just have nothing here under 50. Under 60, we have 0. We have 3 65s. So 65, 55, and 2, 68. Under 70, we have 1, 2, we have 6, $70, sure. Okay, and so on. Okay. Also remember, we need to arrange the value from small to large. Okay, from small to large. Let's stem and leaf plot. It's not used very often. So does the dot plot. So dot plot is pretty similar to stem and leaf plot. Can also give us impression of the shape of the sample, and also have repeated value. Okay. Not generally used in formal presentation. This is the dot plot for the old faithful geyser, the dormant period result. Okay. For example, under 51, we have 4 dots, which means we have 4 51 minutes. We have 1 60 minutes, and so on. Okay. Another example, we have 7 sample values. We have 3, 5, 2, 6, 1, 4, and 1, 7. Okay, we can easily put this in dot plot. Okay. This is another example of dot plot. So let's quality control process. Measure diameter of the gear. Diameter is in centimeter. So I have 15 measurements, but one of the measurements has a typing mistake. Okay. All right. As we can see, if we put it in a dot plot, all the other 14 data is around 1.99. This one, 1.891, is outlier, much smaller than the remaining. Okay. So that is due to a typing mistake. So that is the dot plot. So the third one is histogram. Histogram used very often. Okay, so pay attention to this one. It can give us the idea of the shape of the sample. Okay, and we need to divide the data into several intervals. Okay, and the bars of the histogram need to touch each other, and the space, if that's a space, you indicate that there's no observation in that interval. Okay, so let's show an example. So this is a relative frequency histogram. Okay. The height of the bar shows how often, how many times the certain value occurs. Okay, it can be used use proportion or relative frequency as the height of the bar. Okay, for example, we divide the data into 1, 2, 3, 5, 6, 7 intervals, and this interval should have equal width, normally speaking. Okay, and then under each category intervals, we count how many times. So for example, the first interval, we have 1, 2, 3, 4, 5. So the height is 5, and so on. And here shows the steps how to create a histogram. It's actually pretty straightforward. We'll show an example how to do that step by step. Let's review the steps first. So the first is we need to divide the data into 5 to 12 subintervals. This subinterval should have equal lengths. Okay, so that is important. Equal lengths. You can choose 5, 6, 7, 8, 9, 10. Doesn't really matter. But each interval should have equal length. And then calculate the weights of the subinterval. Okay. So the weights should have a round number, okay, an integer. Okay, round the weights into a convenient value. Okay. And then we should use the so-called left inclusion. Okay, so what does that mean? We'll discuss in a moment. Okay, so left inclusion including the left endpoint but not the right when we count the number. And then we should create a table including the intervals, frequencies, and the relative frequencies. Okay. So the horizontal axis, the x-axis should be the subintervals, and the vertical axis will be the frequencies or the relative frequency. Okay, and the height of the bar shows us the proportion of the measurement in that certain subinterval, or the probability a single measurement will fall into that interval. Okay, so let's look at an example and plot a histogram together. Okay, so it's not difficult at all. So this is the age of 50 tenured professors in a certain university. So we can see the oldest is 70, the youngest is 26. Okay, so between 26 and 70, so let's choose sixth interval. So you can choose 8, doesn't really matter. Okay, and for each interval, the weights, if we calculate the smallest, the youngest and oldest, and divide by 6, so each class should have around 7.3 years. So we make it simple. So let's call it 8. So 8 years for each interval. So 6 classes, each has 8 years. So let's start at 25. So why 25? Because 25 is just a little bit younger than the youngest professor, 26. Okay. Then we just count for age 25 to 33. So 25 less or equal to 25 and less than 33. So this is left inclusive. So this category means if the professor's age is 25, it will include in this category. However, if the age is 33, it cannot include in this interval. Okay, so it will include in the next interval. So we call that left inclusive. Okay. And then we just simply do the tally. So we have 5 professors for between 25 and 33, 14 between 33 to 41. Okay, again, if the age is 41, it belongs to here, 41 to 49. Okay, so we can calculate the relative frequency and also the percent. Okay, so we can finally plot the histogram here. From 25 to 33, we have 5 over 50. So what we can see from this curve, this histogram, so the shape is skewed to the right. So skewed to the right means, so the curve is something like this. The right side obviously has a longer tail. So longer tail on the right side. And we call that skew to the right. Doesn't have outliers. So no professor is much older or much younger than the majority of the faculty. Okay. We can also easily calculate, for example, what proportion of the professor are younger than 41. So younger than 41 is here plus here. So 14 plus 5, or 38%. So what probability that a randomly select per faculty member is 49 or older? Okay, 49 is here. 49 or older is in these areas. Okay, so we can add 9 plus 7 plus 2 divided by total professor 50. So that's 36%. So the probability that a randomly selected professor is 49 or older is 36%. In chapter 2, we will discuss how we can calculate probability for different experiments. Any questions or comments so far? Okay. So right now, everything is pretty much straightforward for chapter 1. This is the example of histogram. It's emission. I don't know what is emission. Maybe the emission of CO2 from a car. So gram per gallon. So relative frequency. That's, for example, 20%. About 20% emissions between 1 gram to 3 gram. Okay, and also the curve has longer tail on the right, skew to the right. This is the Yellowstones, or the faithful, the geyser, dormant period. Okay. Here we can see it has 2 peaks. Okay, one peak is around here, another peak is around here. So this is another example of histogram. This is used for, it's not very clear. It's months, each month. This is the upper limit of load range. I think it's about the pavement research. Okay, so doesn't really matter to us. Just remember, we can use histogram for almost every disciplines. This is another. Okay, so the shape of this curve is very different from the shape of that curve. So this is the skew to the right, has a longer right tail, and this one is pretty much symmetrical. Okay, symmetrical. And this is a histogram of a final grade for one of the final exam. Okay, we can plot that. Okay, so it looks like we have 3 peaks. Okay, so histogram can be used, in many different situations. So we talk about skew to the right, or symmetrical. Okay, so histogram is perfectly symmetric if the right half is mirror image of its left half. Okay. If the histogram is not symmetrical, we call that skewed. Has a longer right-hand tail, we call that skewed to the right. Or we also call that positively skewed. Okay. If it has a longer left-hand tail, we call that skewed to the left, or negatively skewed. Okay. When the histogram is symmetric, then the median and the mean will about to equal. Okay, so very close to each other. So the mean is the average value. If we added all the value together and divided by sample size, so that's the mean. So the median is the 50th percentile. Okay, so the value in the 50th percentile. So when the histogram is skewed to the right, just as this, okay, then the mean will be greater than the median. Okay, so the mean may be here, the median will be here. Median. If it's skewed to the left, has longer left-hand tail, then the mean is less than the median. So unimodule and bimodule. So let's talk about the peaks. Okay, so histogram with only one peak, we call that unimodule, only one peak. Two peaks, bimodule. So bi means two, right? So more than two, we call it multi-module. Okay. So that's histogram. The next one is also pretty commonly used, but not as commonly as the histogram and also scatter plot. This one is called box plot. Okay. So box plots represent the median, not the mean, the median, the 50th percentile. The first quartile and the third quartile. The first quartile and the third quartile. Okay, and also shows all the layers. Okay. The difference between the third quartile and the first quartile has a special name. It's called interquartile range, or IQR. Okay, so that's the value between the first and the third quartile. Okay, so that range, we call that IQR. Okay, so box plot will show this information. And here shows the steps how to create a box plot. Okay. So we just quickly look over the steps and then show you an example. Okay. So first we calculate the median, the 25 and 75%. So first and third quartile. Okay. And then we draw vertical lines so to complete the box. Okay. Also, we need to find out what is the largest sample, which is no more than 1.5 IQR, interquartile range. Okay. We also need to find out the smallest sample, no more than 1.5 IQR. So doing this, we can isolate what are the outliers. Okay. You will see in a moment. And then we draw some vertical lines, we call that whiskers. Okay. For the points more than 1.5 IQR above the third quartile, and also more than 1.5 IQR below the first quartile, they are qualified as outlier. We need to plot each individual outlier in the box plot. Okay. All right. So this shows an example of box plot. Okay. So this one is the median. This line is the median. Okay. This line is the third quartile, and this is the first quartile. Okay. And this point is the largest point within 1.5 IQR of the third quartile. And this point is the smallest delta within 1.5 IQR of the first quartile. Okay, and we connect a point to the first and third quartile. We call that whisker. Anything outside this range, outliers. So we have 3 outliers in this example. Okay, look at another example. This is old physical data. So we put all the physical data, the dominant period, into this box plot. So what we can see is 1, there's no outliers. Any outliers will be occurs here and here, okay, but no outliers here. Also, we can see the sample values are densely packed between the medium and the third quartile. Okay, because this is the medium. This is the third quartile, and this is first quartile. Remember, between the medium and the third quartile, we have 25% of the all data, correct? And also between the medium and the first quartile, we also have 25%. Okay, the distance between the third quartile and the medium is much shorter than the distance between the medium and the first quartile. So we say is, the data is densely packed between the medium and third quartile. Okay. The lower whisker is this one, the line, okay, longer than the upper whisker. And that means the data has slightly longer lower tile than the upper tile. Okay, so it's slightly skewed to the left. Okay. And the distance between the first quartile and the medium is greater than distance between the medium and the third quartile. So we already see that. So this distance is larger than this distance. Okay. Okay. Again, showed us the data are skewed to the left. Skewed to the left. Okay. So we can also put box plots side by side and compare them. Okay, so we can easily see how the medium different between the samples and also the quartiles. Okay, and also how the sample spread. Okay, let's have an example. Step by step. Okay, first we calculate Q1. Q1 means first quartile. Okay, M is medium and Q3 is third quartile. Okay, IQR is interquartile range. So that is between first quartile and third quartile. So that is IQR. Okay, then we draw a horizontal line. So we get a box plot. We get a box. So that's the name box plot coming from. Okay, and then we need to isolate outliers. How to do that? We need to draw 2 fences, the lower fence and the upper fence. So lower fence is Q1 first quartile minus 1.5 IQR. The upper fence is third quartile plus 1.5 IQR. Pay attention to the sign here. Okay, so that's the fence. Outlier is defined as values outside that fence. Anything outside that range outliers, such as this. Or here. Okay. Then we draw the whiskers, which is the line here and here. So whiskers connecting the largest and the smallest measurement that are not outlier. Okay, so this value is the smallest smallest measurement, which is not qualified as an outlier within the fence. And this value is the largest value within the fence, not outlier. Okay. Then we finish the box plot. Okay. So box plot can show us, the outliers, where is the median, first quartile, third quartile, so the distribution of all the data. So is, I will say, pretty commonly used and useful. Scatter plot, I will say by far the most commonly used type of plot among what we discussed today. As a material scientist, we do this in the lab all the time to try to find the correlation between 2 or 3 or even more type of parameters. Okay, so data for which item consists of a pair of values is called bivariate. For example, for concrete block, we measure the strength of the block. We also measure the weight. Okay, so measure 2 things. So that is bivariate. Okay, and we can plot this information in the scatter plot. Every single dots represent 1 sample items. Okay, for example, this is 1 concrete block. X, let's see, is the strength. F prime C, let's see Y, just see, weight. Okay, so this dot means for that sample, the strength is 5 and the weight is 1.5. Okay, and we plot all these sample items together. We try to see if there's any correlation between the weight and the strength of sample. If we see something straight, okay, and then we say, okay, there's a correlation between these 2 parameters. Okay. So if the dots on a scatter plot are spread out in a random scatter, okay, such as this, okay, there's no trend we can find from 2 parameters X and Y. Okay, if the dots on a scatter plot spread around a straight line, such as this, okay, and then one variable may be used to help predict the value of other variable in the future. Okay, so what we did is we do, for example, 100 tests. We have 100 dots, and we found out the correlation between these 2 parameters X and Y. Okay, and we get the trend line for this. So the trend line, let's see, Y is equal to A times X plus B. Okay, so that's the correlation between parameter X and Y. So it may help us predict Y using the X in the future based on this equation. Okay, so we do this all the time. All right, I think that's the end for chapter 1. Okay, so chapter 1, we discussed type of data. Okay, we also look at how to do the sampling, mostly SRS, which is a simple random sample. Okay, so simple random sample is we just pick the sample such as lottery. Okay, we also discuss convenient sampling. Okay, which sometimes we have to deal with that. We also learn about the sample statistics, such as sample mean, sample median, variance, standard deviation, and so on. Okay. We also discuss how we can plot these, different type of graphical displays, such as box plot, scatter plot, stem and leaf, and so on. All right. So that's the end for chapter 1. So we finished that in first week. So the second week, we'll discuss chapter 2, which is probability. Okay, any questions before we dismiss?